Hello everyone, my name is Pablo, this is Daniel, we're both postdocs from the band collaboration, and for the next hour or so we're going to talk about ROSE, which is the Reduced Order Scattering Emulator software that we have been developing. This is the outline of how we're going to do things. If everything goes well, we should reach the tutorial in 25 minutes. I don't want to bore you talking more than that. But I do want to give you the main ideas both from the nuclear scattering in general, just in case you're not familiar with that, and on the reduced basis method on its own. I was going to say something else, but I forgot. Anyways, so this is what we're going to do. What I was going to say is I will prefer that this is a conversation, so if you have any questions, please feel free to interrupt, and if at the end we spend time doing the discussion, I will speed run everything else so we can go to the hands-on sessions. We good? Yes? So the first part, as an introduction to nuclear scattering or coconut physics, we want to study what happens, many properties of nuclei, and one way to do that is to just straight up shoot things at them and see how they react. And in here, in this picture, I'm showing my thing that throws things, the nucleus, and usually what we measure is what we call the cross-section. It's basically how much particles deflect from interacting with the nucleus until they hit a target in our detector. And theoretically, how a theoretical physicists will approach this is we have a differential equation. This is my Hamiltonian, my nuclear scattering Hamiltonian. And that equation has a potential that depends on some parameters alpha. And in this particular case, the potential that we're using is called an optical potential. It looks more or less like this, with some other terms. And the solution to this differential equation is going to be a bunch of waves that very far away they look like sines and cosines, so with a bit of more fancy things. The important part is that to solve this equation, you see this L here, this is what we call the angular momentum. To get accurate results, you need to solve this equation many times for different values of L, and that is for a given value of alpha, for a given value of the parameter. And now that Moses and Osge made a fantastic introduction to how Bayesian statistics, and in the case of the tool SORMICE works, usually you need to sample this thing a lot for many values of your parameters alpha, and that takes a long time. And that's why we want to use emulators. And the analogy that I usually like to give is that emulators are like the I cannot believe it's not butter. You will retain some properties of your thing, in the case of butter, that it tastes good, but it will take away other properties that you don't like. In the case of butter, maybe you're lactose intolerant, for example. So we like to think that we have our exact computation or high fidelity solution, that maybe I need to run it in a cluster, and I would like to run these things on my laptop, or at least finish within a day. And that is a business of emulators. Osge and Moses talk about Gaussian processes, which are fantastic because they're really easy to set up. You don't have to think much, especially if you have built software like SORMICE to do that. Probably you have heard of neural networks, and in this case what we're going to talk about is the reduced basis method, which follows under the umbrella of reduced order models. Now, one key distinction that I want to make is that data-driven emulators, like Gaussian process, usually try to fit directly the relationship between parameters, in this case the alphas, and the observables, in this case the cross-sections. Meanwhile, things like the reduced basis method or some type of reduced order models, they try to go directly through what the model is doing. They are, in that sense, invasive. It takes longer to set them up, and it's a bit more complicated. But the idea is that this thing is going to actually solve the differential equation for you. So how does it work? The analogy that I stole from my best friend Edgar is that this works very similar to how you describe a brick. If you want to describe the dynamics of a brick, you need to take into account the roughly 10 to the 24 atoms that make the brick, and write down the equations, the differential equations for the motions of all of them and how they interact. And of course we don't do that. That's stupid. Usually what we try to do as physicists is find what are the degrees of freedom that matter to my problem. In this case, most likely I can describe what is going to happen to the brick with 3 rotations and 3 translations. Now if I want to understand sound propagation on the brick, like if I hit it, I cannot explain that with those degrees of freedom, I will have to increase it. But this gives you that idea of identifying what is important to the problem that you have at hand. In the case of our differential equation, our operator, I am writing it as, for example, a Hamiltonian an eigenvalue problem, and here I'm putting as an example the harmonic oscillator wave function. You can think that this fellow here, this phi, is an infinite dimensional object. It's a solution, it's a function, and it lives in a very high dimensional space. But as I move alpha, the trajectory, and here I'm only showing it in 3D because it's hard to plot in many dimensions, but the trajectory that this thing is following in that space usually is going to be low dimensional, meaning that I can approximate it with just a few components. And that's the idea, the same idea behind the brick. I want to understand how this thing is changing as I change alpha in terms of just these principal components or most important parts of the variation. And interestingly enough, you can think that now these bases, which is the reduced bases, and these coefficients that are the things that are joining those bases, are your new degrees of freedom, and you can try to understand how they evolve as you change the parameters. This is another cool animation for the harmonic oscillator. This is my solution when I'm changing the parameters of the potential trap. And basically, I can describe the black, I think this is black? Yeah, or purple. I can describe the main curve just by a superposition of two of these modes. And that is the idea that I want all of you to keep in mind. So far, so good. Any questions? Yeah? I'm not boring you? Okay. Or you're very polite and you don't want to say that I'm boring. Okay, so how does it work? I could talk for hours about this, so I'm not going to. I'm just going to give you the quick and dirty summary. The first thing that you need to do is choose a basis. It's called a reduced basis, so you better choose a small basis. And one way of doing that is you go to your high fidelity solver, you solve your differential equation, let's say 50 times. Why 50? I don't know. I like that number. And you get those 50 solutions that in the case of scattering, they look like sine and cosine waves. And you build a principal component analysis out of those to try to identify what are these principal components. And that creates this basis expansion. And the second part is just 2 steps. The second step is you need to write down equations that will allow you to find the coefficients A for any value of the parameter. And that, the way that we usually do this is by projecting these equations into a subspace. And this is called the Galerkin method. And this is the dude Galerkin that we read about and are very excited about many of the things that he did. Now, this is going to give you one equation per coefficient, and then you will have n equations with n unknowns, and you can solve it. And the key point is that this n is very little in comparison to everything else that you have been doing so far. Now, why this will even remotely give you something that makes sense? You can ask me, you can read the paper, and you can read many of the other guides that within the band collaboration and friends we have been trying to put out to motivate the nuclear physics community to use this type of tools because they are so cool. And you will see that later on when we show results and when you do it by yourself. This in particular, which is the Jupiter book that I'm going to highlight, and the reason I'm going to highlight it is because we have several examples with code and the motivation of the entire thing, but it is built in a community effort by a lot of people, many of which I see here. And who knows, maybe if you're interested in these type of things and you want to write a chapter of that, you can help us expand it with new examples. Okay, so before we jump into results and doing things, there is one technical caveat that I need to explain, and it's a bit technical, so if you lose me for the next 2-3 minutes, that is okay. Relax, think about something else. But this is important to appreciate what the ROSE code that we have been working really helps with, which is the problem of having non-affine potentials. Here's the thing. When I have this differential equation, I can think that this is a matrix equation in where I have my Hamiltonian matrix, which is a huge n by m matrix. For example, if I'm using finite element methods, this can be 1,000 by 1,000 matrix. And then I have my 1,000 vector solution, and I'm trying to solve this. In the case of the reduced basis, I have my reduced basis, I have my projection equations. So when I write things down, my new degrees of freedom are just n coefficients. And the final equations that I'm going to get out of these projections look like this. Numbers times my coefficients equals 0, usually an n small m by small n system of equations. You can even write it as a matrix. And that is the key point, that this little n is very little in comparison to this big n. The problem is that if you want to make these projections, I'm using Dirac notation, so I should have said that for non-physicists, these bracket notation means doing the integral of whatever is inside. And that is very easy to do if your potential, your operator, depends in an affine way. You can think it of a linear way, but it's a bit more general than that, in the parameters. For example, if I was looking at a potential that looks like this, see that this is separable between alpha and my variable r. So I can make this integral once. Meanwhile, if this is how my potential looks, I cannot make this integral without knowing the value of alpha. That is where the empirical interpolation comes to the rescue. And the idea that we use is exactly the same as what we did with the wave functions. I'm going to expand my interaction as a linear combination of things, one of which depends on the coefficients, and the other one that only depends on r. And then you build a reduced basis for your potential. In the same way, you just find principal components of this thing. And the coefficients, you obtain them by something called the empirical interpolation. Now, the key point of all this detail, and I'm almost done with the detail part, is that then you can go and compute these things only once. Because this integral needs operations of size big N. So once we are done with that, we can go and play with rows. I'm going to show a couple of results, and then we will go into the hands-on session. But what I want to point out is that this software, built mainly by Daniel, and I want to just give him an insane amount of credit, because all of these ideas, after you understand them, at first they look strange and complicated. After you really understand it, it's like, this is trivial. Coding this is a nightmare, and it has been the work that we have been doing for the last months, so that you don't have to. So later on you will see the details on how you build this, but imagine all these things that you need to understand about the empirical interpolation method and blah, blah, blah. You just come to Rose and you say, hey, Rose, this is my potential. It has 7 parameters. This is my reduced mass, my energy, the bounds of my parameters. It is complex. Please train 10 bases, and you're done. You don't have to think. Now the thing just works. And you can use it to actually do physics. And it reproduces the real and imaginary part of my potential very well. Okie dokie. Those were the main ideas. Now you're all experts in scattering and in the reduced basis method. Let me show you 2 main results of what you can do with this, and then we're going to jump to you actually doing this stuff. Any questions so far? Any clarifications? Please, Kat.
Let's say for like the for scattering, where at each angular momentum state, like if you take them all together, that forms like a full basis, like a complete basis, right? So do you have to train an emulator for each individual angular momentum state?
That is a fantastic question, and the answer is, you don't have to do anything. You can do whatever you want.
Should you?
That's a better question. It's exactly the same thing as you can choose any degrees of freedom you want, but if you choose the wrong ones, you're going to be sorry. Here's the thing. This is my equation. In principle, you're completely right. I could treat everything in here as a parameter, including L. I could just say my phi is parameterized by my alphas and my L, and actually my energy. That's something that we do. We actually rescale with the energy. The problem is that you will need to make a cost analysis of how many bases you need to add in order to capture the variations across the parameters and across the angular momentum. And most likely, I'm going to make up a number, maybe 30, 40 bases will be more than enough, and 40 is way less than 1,000, so you're already winning. But here's the thing, maybe if I just focus one emulator per angular momentum, I can get away with 6 bases, and 6 is way less than 30. And resolving 10 linear system of 6 by 6 is way cheaper than solving one of 30 by 30. And that's basically the question. You need to, and I'm going to show something that is called the cat plot, and we're super proud of that way of thinking, how to evaluate these things. That idea that you have, you go and you try it, you put it on the cat plot, and you can show, yeah, it is better, or no. It will depend on the system. It will depend on how many else, etc., etc. But it's a very good question. Thank you for
like a typical optical potential, like the one you showed, do you have practically what is better to do?
I think, so right now, Roses doesn't emulate across angular momentum. We have one emulator per angular momentum. And I think we did a preliminary study, and it was like, no, wait, Jose, yeah, we definitely want to go with one emulator per angular momentum. And the main reason is because the boundary conditions at 0, for L equals 0, you start like this. For L equals 1, you start like this, and so forth. It changes a lot.
Right.
So it starts becoming annoying for you to be able to reproduce all those things. Not only near 0, but also far away. You assume different, that's what you were going to say. Please, Andy. Say it.
No, right. Not just at small r, but large r. The asymptotic behavior of those solutions is different for each one of them. And reproducing the asymptotic behavior for an arbitrary L state as a linear combination of other ones. Is
Yeah,
it?
it's orthogonal, so yeah.
Yeah.
So, but you just try it, and you put it, and you see what happens.
Right, okay.
So, thank you so much. Any other questions? Good. Let me show you the cat plot. I'm so proud and happy about it. Okay, so, main results. The main thing that I want to give you all, so if this is the only thing that you take away from all this discussion, is that the thing works. It works amazingly well. And by amazingly well, I mean we can compute cross-sections in milliseconds in comparison to the high fidelity that you usually take off the shelf on the market that takes around 5 seconds. So the main conclusion of all of this is we should all just go out screaming and saying we have something that goes 5,000 times faster than the high fidelity. There is a tiny footprint here, and basically what that is saying, and I want to give credit to Dick, who is the person that has been saying this for months, we need, or maybe years, we have to be careful because I could make my high fidelity stupidly slow to then say that my emulator, oh, my high fidelity takes 3 hours because I am really bad at coding my high fidelity solver. And then, so this number, it tells you something. It is important because if I just took it off the shelf, that is what I'm comparing with people that might not think about these things often. But we need a better way to really see in the trade-off, and that is the cat.
Hey,
What-
Pablo,
what?
5 seconds is short.
5 seconds is short for things that take hours, but for two-body scattering, you can, and I will show it in a second, you can change the high fidelity to run like in a second, which is 5, and that takes us from 5,000 to 1,000, which is still pretty good. Okay, so the computation accuracy versus time plot, and it took a while to put the words together so we can spell cat. What do? You grab your y-axis, you put the error of whatever you're trying to emulate, and this can be applied to Gaussian process. Actually, one of the things that I want to do, it's just that I don't have time, but I will do it eventually, is in here also put Gaussian process, another type of emulator, so we can compare everything and see which tool works best for which problem. Anyways, you put your error on the y-axis, and you put time on the x-axis. And then you put a target. Let me say, I'm going to compare with experimental cross-sections. That means that I want around 10% error of things. This should be around 1%, but that's okay. And let's say that I want to do a Bayesian calibration in 1 hour. So I need 1 million samples. That came completely arbitrarily from numbers that came out of my head, but that is my target. So I want something, a computational method that lies within this box. Then you go to your favorite Runge-Kutta or Numerov high fidelity solver in Python, and you start changing the tolerance, and you see the trade-off between being very precise, that means low error, and taking a long time. And this is basically the curve that this thing traces here. And then you turn on rows. And it's like, now we're talking. So what I'm changing in here, all these colors means different configuration that I can have for the number of bases for my wave functions and the number of bases for my potential. And there are many other things that I could change. For example, Kyle, I could go and put something where I'm emulating a cross L. Where is this going to land in this plot? I have no idea, but that's what you do, to go and try it. And the main point of all of this is that you feel very happy because we have built something that works very well. Second, you make a more just comparison because now I can say for this level of accuracy that I want, how much faster I'm actually getting. And it will make it easier to then compare with other type of emulation techniques. So this is the cat. Now, the second part is I want to actually go Bayesian. I want to do a Bayesian analysis, and that is the beauty of the tools that we're building at Band, that they all should talk to each other. So what we're going to do, what you're going to do, you're going to make rows talk to SORMIs, so we can do a Monte Carlo sampling out of this mock data that we created from the Conning de la Roche parameterization for calcium-40 at 20 minutes. Just some preliminary results so you know what to expect. This is, and I'm putting here the high fidelity that you take out of the shelf. Again, this comparison, fine print. But with only 26 seconds, you already get 30,000 samples, and you can make a posterior distribution for your parameters that already is capturing correlations and is nailing the true parameters. Those are in red that were used to generate the data. The more time you take, the more samples you can have. This was done in 2 minutes, and plots already looking gorgeous. You can take 20 minutes, and now you make 1 million samples. Or you can just take 2 hours, because why not, and make the most gorgeous corner plots that you have ever seen in your life. And then you can reproduce your data with uncertainty bands, and you feel very happy because the thing is doing what it's supposed to. This is just to show, comparing to other people that, well, we included, that we have tried similar techniques, and basically we are reproducing what we need to reproduce. One final comment is that these 2 hours is completely fine if you're doing like a research project. The fact that this takes 30 seconds can be very useful though. And the reason is, Kyle will talk about BMX in the afternoon, but think about the possibilities of what you can have if you can deploy these things. That's what we're doing already. If you can deploy these things in a cloud environment in where everybody could access it and say, you know what, I'm going to run an experiment tomorrow, and I forgot, the deadline is coming, I need to know what are the theoretical uncertainties of this. Then you just go to this cloud environment and can run these things quickly to try to get an estimate of what to expect from the experiment, for example. And not only that, the idea will be that as new data comes, we can calibrate models continuously, not having to wait until one group every 5 years sits down and kidnaps an entire computer for 3 months to actually run the Bayesian calibration. So this is particularly important now that we have FRIP and have to do a lot of things with optical potentials. Final thing, we wanted to have the paper that showcased rows and everything for this meeting, and it's my fault. I kept adding things, and people kept telling me, please stop, and I was like, no, we should also try this, we should also try this. So it will become coming soon to an archive near you, and there's a lot of things that we're not discussing in here because we don't have time for you to play with it, but that we can discuss if anybody is interested, and Daniel Odell will give a more detailed presentation on Thursday, Friday, I don't remember. When? Thursday. Okay, finally, we're done. Let's go to the tutorials. Daniel, please come here and help me. We're going to try 2 things. The first one, you're going to build a reduced basis emulator for an affine potential by your own hands. You're not going to use rows. So you're going to have to build your basis, build the Galerkin projection equations, and use it to emulate something. And that will take us like half an hour, 20 minutes, we'll see. And after that, you're going to actually use rows for a more serious project. Anything else I need to say?
Yeah, the only thing I want to mention about the first tutorial is, again, it's not, you don't import rows, you don't install it. You are just going to do the calculation by hand and set it up to see how you reproduce the wave function, or you reproduce the solution to this particular differential equation if you want to look at it more generically. Part of the reason that we're doing this is because we would love for you to get the experience with rows and have some idea to install it and use it in your own research when you leave here. But we'd also like for you to see how easy it can be, not always, to apply these methods and see, see some kind of increase in efficiency. So this is kind of the opportunity to do that. It also gives you an idea of what's happening underneath in rows, and so it's not just a black box, I suppose, so to speak. All right, so we'll say 15, 20 minutes. We will be floating around. Please ask questions, talk to your neighbors, be friendly if somebody's somebody's tearing
actually
up
team
over
up. That will be better if we can help each other.
Right.
Let me, just in case you don't have it, you should. But this is how the first rows tutorial should look like. You should have the link sent to you by email. If you don't, you tell us and we will send it to you.
And
It's online too on the webpage.
Okay, awesome, very good. These first 3 lines, you can completely ignore those, okay? They're commented out, you do not need to uncomment them. Go for it. I need them. I don't think I'll need to. Do we need to?
Somebody can come and show. Whoever finishes and can request means nice cream. You can.
this sort of thing is best done when you're interacting with somebody nearby. So the fact that it's so quiet in here means you're not doing
We do have a whole, list of very uncomfortable That's right. Trust falls.
I am.
Yeah.
Back and forth.
And then really small.
This is yeah, so because we have some points.
Oh, yeah. So, okay. All right. So then, yeah. So it's
Yes.
I think that's probably true. I don't know whether I am. Oh,
nothing. Problem resolved. Yay! Now we're doing the company.
Group projects.
Where we're totally both and we're Yes. One second.
The next part, the last one.
Doesn't matter, right? I can
This is actual.
So one So what did
Right. Yeah, so what do they This is very much.
That's just a trick for
It is not just the trick. I would say it also, no, it's fine. It's not just that, but it does, like, it's kind of, it makes the basis.
Oh, yes.
Because as long as we're training in the right space, reference experience or anything. Recently done this. I don't remember how we.
Well, so now you get the asymptotic dimensions.
Okay.
I want to plot this line over this line and see how it changes. Because the hard part with this start off and start to.
Yeah, so the hard part with bounce state.
Right.
So you try and
Maybe it was my guess is some similar notes. With the bounce state, right? Where
You have to believe.
I was actually trying to emulate and because I'm just wanting to use this to find bounce. And some people are just
So that is the hyperlink,
Okay.
the one that is not super.
But
Now you have to one from
5-0. I kind of was interpreting it as like quoting something about the boundary conditions.
yes,
But it's
yes. That is also
You do it and explain it.
Yeah, I mean, sometimes
Yes.
try to find some filtering. So you is a main, you is one of the vectors, he is one of the vectors, filter the other vector.
Okay.
But you won't see that. I mean, you'll get different solutions.
Sorry.
So in this case, it's
Wants to work really well.
regardless.
Yes, we wanted to limit that because it does not go down yeah, for each order of magnitude.
You know something
So it's
No?
Yeah, so we need some shorting equation exactly like 100 times to get one
questions, but it's more
and then
SVD question.
basically after that these functions will form the base of reduced subspace and we need to project onto that and then solve the eigenvalue problem inside that. Right. I don't know what this thing is doing here. Why is the change? That is the piece of
And now you need to build your
Yeah,
system.
so these are training points you did a singular value of decomposition.
What these plots is telling me is how important each expansion.
What you find is that the eigenvalues are not a whole bunch of the same, but typically you'll find that they really decrease. So you think about diagonalizing this thing and say, let me find a better basis. Turns out to explain most of the, if you see something that's exponential, which is very common on that, you are explaining most of the information in this just with a small number of bases. Okay, so you can think about it, you can have a whole bunch of things that have redundant information. SVD sort of picks out what's worth with PCA will typically use SVD. So the general thing, so do you know about SVD? This is something that is like the most important linear algebra thing to learn about, and they never teach that in the linear algebra courses that physicists have. Never. So if you imagine one thing to do with these, for example, if you want to do so I actually have notebooks that you just, by the way, that I can point to. Take a picture of that. Right? And
cellular rates are these actually,
use that as a big matrix.
okay, so this makes sense. Are the reduced basis metric. If you take
Do an SFE on that,
these later trains,
you
with
keep
these 4 stars,
the kind of keep only some of
like
those
training you was those 4
things.
no,
Maybe a small fraction of the number of. And then you keep those stars instructed. What you have is a lower resolution image of itself, still recognizable, fractional. Probably done that in different.
That's the only thing that the emulator and the
You get a bunch of different things.
because
Do a Fourier transform in that. And you say, okay, the high frequency. So you do a low pass filter on this. And you set the same sort of thing in terms of this whole idea of
transpose the reduced basis the training. When I say training, was
So once you do,
you gotta learn about SVD.
it's happening.
Oh, no, it's really,
That's why it's a way more just an information, because I'm training with solutions to the differential equation. Gaussian process.
I was trying to relate this to be very,
So
if I have multiples
might not want to do
of the actual analysis, and I'm finding the axes,
but it's very fast and very different. That's what you're learning.
So if you use
Singular
the theta
values.
0 and theta 1,
Yeah.
that's not as efficient
So my
as.
recommendation is trying to go to
the direction along omega 0, where you for very small variables, the direction along
This is my
omega
favorite
1
topic ever.
captures most of the
I'm more
variables.
than happy
That's
to
what I was the largest singular variable, right? I can't remember, that's what I was trying to
Because it's all of the inverse.
that's why I'm asking you.
right.
You know, so I just because point being it doesn't have much variation. There's not a lot of
Exactly.
you want the ones that you can nail down in the direction the large vertical axis. That's where all these.
I was trying to get you an answer on that. I'm pretty sure it's the value of this, what this primary y-axis corresponds to, either a variance or one of the That's
She also wants to
Last time I saw like a really detailed y-axis.
So I don't know why it's not on the.
Right, so like you can do this, you can do this for your MCMs, like if you're doing two calibrations and you have a chain, right? Maybe you have different parameters.
This is your point.
Do before you do
0 and
CA,
scale. It's one Gaussian and another one that kind of your rate. That makes both parameters that makes the size of the way. One of them is goes down and the other one goes up.
penalized.
You can change both of them because they're both negative.
There's that
One
there.
very big, one very small. At the end of the
That's not
and then it just gives me a free particle. Yes, I don't go ahead and try to bring this right. Why there's such a emulator is actually bad.
Has anybody actually gotten to the end? I'm just curious. Yeah, all right. Good.
Well, of course,
Oh, yeah.
Yeah.
Oh, yeah.
Nice to meet you. Yeah, I think I saw your talk on
oh, back in
October or whatever, but I don't think I ever got a chance to meet you.
Yeah, well, nice.
You can. Why don't you try and change it? Add an extra.
So I just did LA Curves 1.
Well, it does.
It didn't work because I made a light. You could just change it, but if you go down where these solutions, one problem. The other problem, which I didn't realize, is that when I assemble the operator,
Oh, yeah.
I don't actually have any. I know that you can create that.
Yeah. Like in 5 minutes, we're going to switch to rows.
There's an image. Great scale, there's some number in each pixel. we're gonna do the SVE. We'll just and we're going to see that
Very well done.
and then
We will be switching to the second tutorial in 2 minutes. Sit in the back and yell.
48.
Like my gallery.
That type of thing is I really recommend that. How are things working here? Take this time.
Yeah, we're gonna
Alright, how are we doing? Touch your computer. Hands of people that have finished. I already got a couple over here. Got it all the way at the end. How, yeah, like, if you're more than, say, 90% done. 80%? 70. Alright.
Oh, you want
to give somebody an opportunity?
yeah, let's switch, and that's part of the appreciation.
Straight from there.
No, I drove from we got 90%.
You stole. But I'm not sure how they.
We can do it at so let's reduce the second mile, and then you subtract it. You already have a partner. We need to talk about this.
Alright, so what we're going to do, just for the sake of time, we have about 40 more minutes, and people are going to start
30 more meters.
30?
No, 40? 30. Ah, yeah, you're right. 40. My bad. Sorry then.
People are going to start getting hungry and
Yeah,
moving.
yeah. It's finished earlier. I'm hungry.
Yes. So, if you didn't get a chance to finish it, there's plenty of time this week. We'll be around. You can ask questions. Again, try to think of areas, things, calculations that you're doing now that you could take and maybe learn from. We're going to move on to the second tutorial where you're actually going to install and run with rows. Those first few lines are important. So I want you to go to the link for that second tutorial that Daniel Phillips sent out, and I want you to follow the very clear instructions at the top. And go to the new notebook that has been prepped for months and wasn't assembled and finished last night. And I want you to run with that one, okay? Because that's the one you're going to actually import rows. You're going to get as far as you can. What you're going to be doing is helping out physical system, calcium-48 neutrons.
Ah,
My favorite. So what you're going to be doing is setting up an emulator where you train to emulate the scattering reaction of calcium-48 and neutrons, and then you're going to create one of those cat plots. It's not going to look exactly the same. Challenge to you if you can explain why. But it'll similar important features, and then hopefully you can do a Bayesian calibration. We'll see how far we get.
And part of the main lesson out of all of this is appreciating how nice it is to have such a tool that can do this for you, given how hard at first it is to compute many of these things. Yeah, that's a picture of us yesterday. This is how it should look. Be sure to run this part, and we'll be walking around.
If you have any problems here, please don't hesitate to throw your hand up.
And
I
Daniel
say
will
that
help you.
yeah, I say that confidently, like I'll be able to fix it, but I'm good at commiserating, so good luck. Get started. Let's not.
Yeah, so that's just comparing to like the true high bellies. Did you?
Oh no. But I have
Oh, the solve?
this other,
Yes, it's not. So I think you just solve SC alpha star.
this parameter P is 0. So this term doesn't matter.
Oh,
In this example, I actually do.
Important.
Okay. So, and I was.
Yeah, I did that with mine because I used this version of Tower Road.
We had to make a specific branch. I'm looking at Pablo's special hacks that
Yeah,
open up.
I think.
Yeah, no, I was like worried that what would happen with mine, so I was like, I'm not touching anything.
Yeah.
And then I couldn't
It was
test or anything, but like,
Lost it.
The funny part is that
Your base is not.
life, because it's something we did together. When things
Yeah, I guess when we were right. I still can't figure out what's in the air. I mean, there must be some calculation in energy frames, but just
great.
my guess is, remember, I took the energy out of a lot of those. I bet I took it out somewhere, and it's still calling it, or I don't know. I can't figure that out.
And you're also super encouraged to talk to your neighbors.
Well, you were really helpful and
that you left me behind the This is just method all the time. This tutorial is a mathematical.
I copied your code.
Yeah, I
The number of nodes. Yeah, so that means you're external.
And you have to take the only thing you can do is keep in the space of parameters. Parameters like space. Otherwise, starts to different 3, 4, 5 multi-dimensional film things here. How should I take? You might think that, oh, I should put them on grid wall. That's a terrible way to do it. Oh, okay. Often you will do something I think it's mentioned in Latin hypercube. That's kind of so that Einstein yeah, you imagine
Alright, so it looks like sounds and looks like installation processes are going okay. Things are okay. Fantastic. So if you get a little shift click happy, that's fine. But so in this case I want to be clear that like, we're using an optical potential that's taking advantage of all that empirical interpolation that Pablo showed, and I think it's using up to like L max equals 11. So each one of these emulators is on the side. If you pay attention to your RAM, you can actually see how it's not big use as you get. But I was just trying to, it's a more realistic calculation than what you did.
some of them may be redundant.
Oh, okay. Well, so luck that Daniel is here who wrote this notebook.
What had happened?
no, this is on the last one, this one.
Oh, yeah, okay.
I need it, I just don't understand what
This part?
Yeah.
Yeah.
What you have.
So,
Well,
the idea is,
Probably sometime this week, someone will.
okay, so you have these coefficients now, and you have basis expansion for the emulated waveform.
You made it so it's all negative.
I have a great card. The numbers of holes. Oh, sorry. The number of questions. This is not documented yet. There is no way you could have known that.
The most important thing when you're out and
Yeah, see what happens.
somehow they never teach you physicists, I guess, like basically essay exposition, famous one by a guy.
So if you go to the
That's a really
now by your
intuition, details,
I want to know NMAX and R1.
physical picture of what's going on. Intuitive.
I don't want to shoot 50 questions straight and then do it to you because I might as well just put it to maximum max.
I really suggest.
yeah,
What's the word?
Yes, yeah. General decomposition of
These four numbers
associated with it are these things called singular values, which in
what if I change
special cases are just the eigenvalues.
what do you expect?
Yeah, I mean, it's probably correlated to
But it's
that.
more
500
But on the other side,
these parameters.
Think about diagonalizing a matrix eigenvalues. And
If you 400 of those,
use that to figure out the best base.
so what's the difference?
all of these
Start with here that there's a lot of
that
direction.
basically
Don't count very much.
400.
something.
even side if you have a mode
I want more valuables. Basically, I want to just see how that
Extend that to many dimensions. It's hard to figure out.
as I change that parameter.
And I wish I
Picture of those the exact same way.
and
What is for you different?
And then you have
convert it to
what is the
great.
so there are two
From
very brain leaps on doing that. The first one is realizing we can do the exact same thing for the waveform for my operator. And actually the way that error is that we are never approximating to the we're approximating an operator. And that's a very nice way of thinking because basically that idea is saying this operator is a huge matrix that sends different vectors from a three-dimensional space into another dimensional space, blah, blah, blah. And you're going to grab that operator and you're going to construct the operator itself. And then of course the solution is reduced with it, but the important part is the approximation of the construction. The first brain is to realize I can play the same game that I played, the wave function, so now we can reconstruct it. Now, the next brain game is how to
small fractions of
image what are you going to do for this one?
That's just
You do have
sometimes
the explicit expression. Like you have to solve the equation that you get why is it what's the value of this class. You get it? You use empirical interpolation method, which is saying I'm going to ask
this is a deep
n questions at n location x, and I'm going to make my approximation interpolate between
time.
and I truly believe in low dimensional mind. That's basically your approximation.
General observation is that
That's exactly the
descriptions
Now, quoting that is a pain.
in general
There's a lot of moving pieces, and Daniel is
have a lot of superfluous.
super mega cute.
no.
That's why in this tutorial, we're not asking you to do that decomposition, we're just lots of rows, less of rows, will be important. So now we're having some freedom in this tutorial, it's not some very rather it's the level above row, telling rows to build the things and then use those to wider coverage.
So actually, maybe that if you think about things that describe
Also,
order, I'm going to pick an example that I don't know if you need it. Sure. The Eisenhower. Eisenhower is a lattice of spins.
Am I doing
And it just spins up and down. And it's a model for
Yeah.
ferromagnets. So,
Yeah, it's confusing because sometimes
this model
data
will solve it, you'll get phase changes.
means
At low temperatures, they all line up. High temperatures, they're random. Actually, there's a phase change.
doesn't know when.
Although thermal very well. So if you imagine that as and you would say
So I
every spin
feel like when the problem is
could talk to every other spin.
super fast, when it's not
And every one of the strengths of that interaction is different. That's the general thing that happens in the neural network. What describes something which you only talk to nearby ones, and everywhere you look, it's got the same pattern. Exactly. So you go from something that has n spins, would have to the n possible constants in it.
Well, I wouldn't have gotten it.
Things where there's one constant, which is the constant and you only do for example, that is the observation that real world are like that, not like there's nothing that looks like this other one.
Right, because you can, right? You don't
This is the
have, but
thing
if you,
that
yeah,
this is the thing that
yes.
machine learning and neural no free lunch says that basically said if the world were like all these
No, you don't.
there'd be no point
I don't care about what
these
is
models. All you could do
So long
is
as the difference
you never learn anything because everything would be
the fact that your position starts with race doesn't mean that my RBM
how many experiments probably in order to understand this? The answer is
and at the end
Yeah, because it's not
So-
in the
so
stat
very
space, right? You're using the space
whereas our
behind that
observation
space,
is
to use a weird
Yeah,
terminology.
yeah, no,
To
that's
get
very
it.
much.
Okay,
anybody made it down to the cat
this
plots?
is the underlying,
Imagine the cross end.
So it does have
We have noticed
That just happens and now it's
some of them are in the box.
this is eigenvector continuation system. That's special.
Last night that was on.
parameters to observe on the physical one, and you don't have any information of their symmetries. How is your spectrum going to know that it is pink? This doesn't care.
But this is
So long as the
like
solutions
say I,
to the equation
I'm going to have
are still approximate by linear superposition, you actually get away with the thing, and that's what
there's
emulator is that you're training these regions and you start extrapolating like crazy and they don't care. The accuracy increases specific difference. They're still able to extrapolate.
unreasonable effectiveness of mathematics
Follow everything.
and science work.
Okay, because I have the two pieces.
And basically what the late machine learning folks who are physicists
Can I
are
draw?
doing saying that
No.
draw,
the analog of this
Are you familiar with this or
is having
your new intellect? Are you familiar with the
Analytical equations.
So this is a method that uses
they're basically learning this thing, good ideas for physics.
Oh, okay.
It's going to be
This is
very profitable to understand how
this explicitly calculates right? Whereas they use it
You create a predictor function that knows about standard deviation.
So what
right?
can you tell me?
The solutions you already know them by heart because they look like slight down.
One of his
Square maybe it looks like the right? And then lambda
oh, these are the
either also or I think it's for like the end. There you go.
I don't understand why this cannot work.
Training it on?
Yes.
Let's say eigenvalue.
Yeah.
That's about the count. So you're running
Right?
a function
And I could emulate
on the
it.
points that you
I should emulate lambda versus alpha using a Gaussian curve. How do I do? Solve the problem with and I have my linear Gaussian.
Because you might not accept.
throw it away.
Properly. Not while we're doing it. We're doing it.
This actually,
I don't very good. You still have to do a lot.
The radius is 1 kilometer, so it's very like only
And I'm going to look
hey there, how are you doing?
oh, weird. Oh, maybe orange.
that I can in trouble.
Oh, because this is just
So these also have to evaluate the library. So it has to evaluate what they everybody knows.
And now the question is, whenever you compute a new alpha,
It's a trade-off.
are these that make the best approximation, right? So that is just by grabbing the entire operator.
That's like all the way across.
Oh, it might not be.
You want this equal to 0, but you know, since you're restricting it to these, but since you are restricting your function to the number here, because of here, you cannot. We're restricting it.
say you want to pure
Zero.
with a function.
Let me project it. And say that the projection is 0. This is not 0, but the projection is 0. On these 5 psi 1 that I just made. And let me do the same with the other side. And also requires and now I have two equations. I just plug in the value and put it in. Find the conditions and projections by 0. And I add one more condition that is that phi hat with itself here, it should be 1. It should normalize. And this process, now I have 3 equations, 3 unknowns. You give me a value of alpha. I solve it, I put it, and I can obtain my lambda hat, which is the approximation of lambda. And I get an entire curve. I don't get points.
It's nice.
And it's just so much better.
Yeah, thank you.
Show you.
My wife since we've been in that, so that's there's not as much to learn.
What are we doing over here?
There's a map which we unit distribution.
There is?
Yes, there's only so many school buses.
I guess maybe.
Yeah, that's reproduced.
I know we were running
There you
right
go.
over
Something you
For sure. Like if you check, if you go back and check that.
Here I'm showing you something that is almost this, but it's one more layer of complication because this is a harmonic oscillator that the particle interacts with itself. It's trying to mimic.
What I haven't told
It's trying to mimic self-interaction. Doesn't matter.
for a real value distribution like that. As opposed to
Kappa is the matrix strength.
complex value distribution. But it seems like it's still works.
The emulation is that they look super well on each other. In fact, our collaborated. The main point that we made is the training region was more stars that are inside that.
Go out that far.
Then you extrapolate on the things. Why? Because these are extrapolating in they use extrapolating in the region equation that is happening behind. And that is so much more information rich than this. And the first thing is that I saw people doing things like this. I remember seeing this and being like, you are lying. I don't believe you. I don't believe you that
There has to
no.
be a point out here that I'm going
Yeah.
towards.
It's like, no.
You
Because
need one.
you think that what I'm extrapolating is that, but no, it's not. It's a different that now I have wasted all your time in that. Okay, later, he's doing all these things applied to Odell scattering super fast and easy. For the level of accuracy. You can apply it to all the things that you're doing.
This is a really juicy stuff.
that this guy
It's like the other, like
is oriented this way,
But you don't have a close.
and this one is pushed, pointed that way, and this one back the other.
I love this topic. As you saw, I can talk about this for hours. I'm not going to bore you with definitely everyone with the code if you want. If at some point you have questions and you don't want to think about how you could apply similar emulations to your project, you seek me out.
That's
me
I mean, that just means
make some changes.
what does it mean one's going this way and one's going that way? Yep, one's correlating, one's
No, we're sitting on this.
and the ones that are
Still,
unslanted are
I don't know why it's so easy.
different ways, so you could produce
So
correlating
that
emulations.
what? It's stuck in for a while.
Okay.
Basically.
Well, as long as it isn't started.
oh yeah, no, we can answer why.
Okay.
Because that, what that is making is different
But
calculators
Yeah. Oh,
with
okay.
increasing precision. So the last one takes one.
Yeah, I mean, when you showed it, you have the counting rate, so it's not just one. It's, oh, okay, so the last one.
What mattered was how round it was.
you have, yeah.
So matters is how slant out. So in other words, if I had those things.
Those colors, and the way you define that, I asked her, give me a list of 10 colors that you think, yeah, give me a list of 10 colors that you think.
If you could just make gauchos, that'd be
Give
pretty.
me those, and I'm like, this is
Yeah, that's a good idea, because like after I use black, red, blue, green, I'm kind of like fumbling.
Or if I took something that's round, for me, I could just change the scale on this axis and then it's flat.
Look at that.
It matters.
Yeah, because that was.
Yes.
Yes.
There it is. Oh, I see that.
It looks different than mine, from anywhere.
I think we're using two
Great
emulators
job.
here.
Now you can select your reduced basis.
Yeah, we've kind of just.
Emulator that you want. You see, I'm changing, see that I'm changing number of videos.
And then
If you select the 3D, you're out of your yeah, but you see that why is it changing
Right, so you just pick this one.
For example,
And
yeah.
then choose one.
Yep, yep. And that's the idea, that we do all this such that you, the user, just sit down and be like, this one, this one, this is the one I want.
Right.
So in a situation where I wonder if it could also be
Very good listening, so happy. So there.
once you've done a lot of you could train.
I love the customer.
If there's a use to it.
So, why are we not why are we using a document? You can see where there.
Yeah, so print, why don't you
Numbers are different.
Right?
So, it looks like we're training an emulator to pretend to be the high fidelity solver instead of using the high fidelity solver.
Each time
So, I was thinking,
I don't know why they're
more power
is there not more? Or it may be that where are they? Oh, you mean by alpha. So by alpha is your list of solutions, not your base. You solve the problem on your base.
but it is like basis. You don't really need the emulator.
Yeah.
You just need basis.
Let's see.
Which we could have.
Well, okay, maybe they just
So Rose has
I know that somehow
class that will let you just grab solutions. But it's kind of easier this way, just to have an emulator that also has instances. It's in the emulator slash, it's in the list of partial weight specific emulators. Each one has a basis and so forth.
Yeah.
It is using a high fidelity solver. to
Basically,
generate
what I think we should have the time
from which you calculate.
two options, either use or
Well, I like rows because
because the judges are basically taking
I think here if you were to explicitly
right now I don't know if I
mathematical documentation is
Before the recap,
yeah. Okay, so in 3 more minutes and then we have to
3 more minutes?
So we should stop at 45, 32.
Yep.
3-4 more minutes and then. But it will be nice to have questions.
Questions?
Yes. How many should
Yeah, I think we should.
I got brief on that later. So I need to talk to Kyle about his power because when they were talking about like, oh, they're surmised and rows were together, and I'm like,
I had a random thought even on one of my phones. And I was comparing my notes. We should be continuing an example now.
These are replaceable.
Maximize the power.
okay, yeah. Or do you like, I don't know the word, what do you want to call this, like?
You just do a two-step approach.
Right.
Where I have some data, some of it will go towards evaluations, and then the rest will go to basic. That's the current setup for surmise.
Okay, because I was curious if you could do like
amazing.
corner sync calibration.
I have no idea what they
At the
mean.
same time, or if it would have to be changed.
But identify ability and the calibration parameters.
Okay, yeah, because I haven't done this yet, so I know you guys have been playing with it.
It's really hard unless you have very specific problem. Pretty much where you're like running into this or something. What if like the high fidelity training points that run in order to have an emulator? Just because it's too expensive. Like what if you can't even generate the training data?
I was just trying to check whether things are overfit or under. Alright, we don't know the answer.
We are regularly asked about signal sections from these papers. These are not 60.
Okay.
Yeah.
Yeah, but like, if you see that has how, where you said like either emulate something, use that, or calibrate something.
The question is, where are the contours? Maybe it is.
Sometimes we read at 38. This means that when it wants to the Gaussian, they 39% lower. Therefore, the relevant is 39.
Yeah.
So you're right.
My question is,
No, those are over.
which one, I don't know, which ones are overfilled?
I agree. Yeah, because the plot that they should keep, since I corrupted the data by that 10%, it should be outside of the center. And how much outside? And I think
That's what we're just looking at.
I think you're right, and I think it goes by half 6. So just count in that way, and it should be within the computing you have.
So this is
What exactly
So I'm going to close so we can have some time for questions. Finish there, and then you can.
Basically, you have some data that we generated. You have some data and you have a model that will draw curves through this data. The calibration stage
Everything is
is using CMC, trying and guessing a whole bunch of different parameters to see which ones draw the best curves. And then it stores the ones that, this is a very bad simple explanation, it stores the ones that do a pretty good job. And it gives you a relevant distribution to show how well
so that one, what happened is
so those posteriors that you get are just various parameter distributions, ranges of values for the different models.
more than overfit is just that audience algorithms are taking into account. It's just that my points still landed exactly where they're supposed to land. So that's the and for this example, I just rotated it.
Yeah, so you can, the idea is you might come to some conclusion that this model does a good job, but being able to quantify the predictions from that model, especially since most of the time what we're doing, you said chemistry, right? Yeah, what we're doing is learning what we can where there's measurements, and then we take that same model, the same parameter distributions, and guessing somewhere else.
I think it's 39 predictors, so 68,
Yeah, we want to be able to have quantified errors.
we should.
We enjoy working with you. This might not be a quick one. We just had some
Well, everybody, we're going to pause now working on our laptops because we have 5 more minutes. I want to be able to show you how many of these things look in case you were not able to get through that. And we also want to have a small amount of minutes for questions and discussion, and if we don't have any, we just go on it. So, how many of you were able to actually go through the entire second thing and get corner plots?
Hey, not bad.
Oh, very good, very good. Proud of all of you. Those that were not able to, that's okay. Don't feel bad. You have more time later if you want to continue playing with it, and we'll be more than happy to help you on that. In here I have my cheat sheet of how this runs in my computer, and I'm going to show you so that you can compare with yours, and it will be interesting to see how Google Colapse goes with this computer. As a quick reminder, these are the type of things that you now have to deal with, and that's, by the way, that's part of the lesson that we wanted to convey here. This first tutorial, your degrees of freedom as a researcher, you needed to put all your time and effort into these detailed things. And the idea is on the second one, you can start thinking big picture and just let Rose deal with what is happening on the trenches, basically. Anyways, if I go down, these are my cross sections for the 50 test cases that we looked at, and this is my cat plot. And my cat plot might look more to the left than Google Colab, and that's fine because, well, Google Colab is free and this laptop was not. And I was going to say something else from this one, I don't remember. But, well, this is a picture of a cat, if you didn't have one in yours. I actually have one of the first plot that we made. These literally look like a cat, and they make a contour on their entire thing, and then they were mad at me.
I think the improvement in time is a big deal, right? You can see that you have some different parameters you can tweak to get the same accuracy. But right, what you want to see is that, I think one of the most important things, right, is that it's categorically better. It is on a different, right? No matter what you do to the high fidelity solver, you're not going to get down to the region that you need, right? I think that's
very good.
I just wanted to make the puns.
Yes, it is, of course. The idea is, yes, of course. The idea is that once you look at this, you select what is your configuration, and you say, okay, Surmise, this is the emulator that I'm going to use. In this case, we selected the 1414, and we basically just roll with it. And after you do all that painful work, this is the final result that you get for, like, I don't remember how many, maybe 50,000 samples or 40,000 samples, which again is great, even this type of rollers that you can get that really nice. And that is all. I think the last part, well, you can see the chains and you can see your plot and feel very happy about it because your points are not exactly on top of your curve, but they are within the statistical uncertainties that they are supposed to. Having said all that, we have 4 more minutes before we have to back off. Any questions, any comments, any wishes for the future on, we're going to focus on finishing the paper and adding documentation to all of this so it can be more useful. And eventually, of course, we're going to jump into other types of physics problems to apply these type of techniques. But anything that you want to share with us? You want to share something with us? Yes, of course.
So the one thing I wanted to point out, the way this is set up, you generate high fidelity solutions and you save them, and then we actually reuse those same solutions to train different configurations of emulators. So that makes it a little easier to save all these things and only do them once. But it also highlights another feature that we built into ROSE, where maybe you don't want to use our high fidelity solver, or you have your own that you think is better. So part of it is there's two ways I would say to approach using it if you're considering using it. You can define an interaction and let us generate the high fidelity solutions, or you can just say, here's my wave functions that I've already got. You don't need to know what the interaction. Actually, you do need to know the interaction. That's the truth.
You don't need to know the solver.
You don't need the solver. But you can provide your own, right? And that's something that we built into it. So that made this, I think, made the notebook in some cases a little bit longer than maybe the simplest case, but I think it showcases a lot of features. All right, your comments and questions. More important.
Oh, sorry.
I also do the same.
Yeah. Very well, the good news is that we're going to be around for the next week, so this is not the last time that you're going to see us. If there is no comments or no questions, I officially declare us done. I'm very happy to have shared all of this with you, and let's go eat because I'm starving. Thank you.